You're asking about algorithms that are robust to imbalanced datasets. It's important to understand that while some algorithms are inherently more robust, the key is often how you train and evaluate them, using techniques like cost-sensitive learning or appropriate metrics. Here's a breakdown of supervised and unsupervised algorithms and how they relate to imbalanced data. Supervised algorithms, with considerations for imbalanced data. It's less about the specific algorithm and more about the training techniques used with them. However, some algorithms are generally less sensitive to class imbalance than others. Tree-based algorithms, decision trees, random forests, gradient boosting. These are generally quite robust to class imbalance because they learn hierarchical rules that can focus on the minority class even if it has fewer samples. However, they can still be biased if not handled carefully. Explanation: the tree structure allows them to isolate minority class instances in specific branches. Support vector machines, SVMs, can be effective with imbalanced data, especially when using cost-sensitive learning, assigning higher costs to misclassifying the minority class. Explanation: by adjusting the cost parameter, SVMs can be made to prioritize correctly classifying the minority class. Neural networks, with modifications, can be used with imbalanced data, but require careful training. Techniques like cost-sensitive learning, oversampling, undersampling, or SMOT are often necessary. Explanation: without proper handling, neural networks can easily be biased towards the majority class. Key training techniques for supervised learning with imbalanced data. Cost-sensitive learning. Assign different misclassification costs to each class. Higher cost for misclassifying the minority class. Oversampling. Duplicating samples from the minority class. Undersampling. Removing samples from the majority class. SMOT. Synthetic minority oversampling technique. Creating synthetic samples for the minority class by interpolating between existing samples. Ensemble methods, with modifications, combining multiple models trained on different subsets of the data or with different sampling strategies. Unsupervised algorithms, less directly affected. Unsupervised algorithms are less directly affected by class imbalance because they don't use labeled data. However, if the imbalance is extreme, it can still influence the results. Clustering, k-means, DBSCAN, hierarchical clustering. These algorithms try to find natural groupings in the data. If one class is much larger, the clusters might be dominated by that class. Explanation: the density and size of clusters can be skewed by the imbalance. Anomaly detection, one-class SVM, isolation forest. These algorithms are designed to identify rare events or outliers. They are inherently suited for imbalanced data where the anomaly is the minority class. Explanation: they explicitly model the normal data and identify deviations from it. Dimensionality reduction, PCA, t-SNE. These techniques are used to reduce the number of features in the data. They are not directly affected by class imbalance, but the resulting lower dimensional representation might still reflect the imbalance in the original data. Explanation: the variance captured by PCA, for example, could be dominated by the majority class. Important note on evaluation metrics. When dealing with imbalanced datasets, accuracy is a misleading metric. Instead, use metrics like precision, the proportion of correctly predicted positive observations out of all predicted positive observations. Recall, sensitivity, the proportion of correctly predicted positive observations out of all actual positive observations. F1 score, the harmonic mean of precision and recall. AUC, area under the ROC curve, measures the ability of the classifier to distinguish between classes across different thresholds. By using appropriate training techniques and evaluation metrics, you can effectively handle imbalanced datasets with a variety of supervised and unsupervised algorithms. The choice of algorithm often depends on the specific problem and data characteristics.